140 prijava, a dio nas moći će pratiti dakle, preko online snimke koja ide direktno, što nam je tehničko učilište u Zagrebu omogućilo, a snimka će biti dostupna i naknadno na našim stranicama. Ovoga puta, s obzirom na temu, predavanje se održava pod pokroviteljstvom Ministarstva zaštite okoliša i energetike, a iskoristio bih priliku zahvaliti našim sponzorima koji su podržali financijski ovaj skup, to je tvrtka Containment i tvrtka Montera, svaki sa sortimanom proizvoda koji su usko vezani uz ovu našu današnju temu, dakle vatar, polines, Containment i konkret kanvas i pensar ispred tvrtke Montera. Osim svih nas, geotehničara kojima se time bavimo ovdje u Hrvatskoj, koji se okupljamo oko Hrvatskog geotehničkog društva, predstavljamo svoje tvrtke i institucije. Danas ja bih htio pozdraviti i zahvaliti se na dolasku i našim gostima iz drugih institucija. Tu su dakle predstavnici Ministarstva zaštite okoliša i energetike, Gradski ured za strategijsko planiranje i razvoj grada Zagreba, Hrvatska komora građevinskih inženjera, Fond za financiranje razgradnje nuklearne elektrane Krško, Sveučilišta u Gradu i naši dragi gosti iz susjedstva, Fakultet za gradbeništvo i geodeziju Univerzita u Ljubljani, Zavod za gradbeništvo Slovenije, Građevinski fakultet Sveučilišta u Beogradu, Institut za istraživanje materijala INIS, Hrvatsko-geološki fakultet Univerziteta u Beogradu, Saobraćajni institut, Arhitektonsko-građevinski i geodetski fakultet iz Banja Luke. Pa evo, još jednom srdačno svih pozdravljam. U ime domaćina pozvao bi izvanrednu profesoricu, doktoricu Lidiju Hrnčević, prodekanicu za nastavu i studente, da nas pozdravim. Hvala.
Honorable Professor Rowe, ladies and gentlemen, dear colleagues and students, it is really a pleasure to welcome you on behalf of our dean, Professor Leakage, who unfortunately couldn't be here due to previous obligations, and on behalf of the Faculty of Mining, Geology and Petroleum Engineering of the University of Zagreb. With rise of global consciousness and environmental protection awareness in the past century, environmental protection has been embedded in industry activities for the last 60 to 70 years, especially industries like mining, like petroleum industry, which strongly base their activities on strong interaction with nature and the environment. As being the only higher educational institution in the Republic of Croatia that conducts studies in mining, geological engineering and petroleum engineering in the field of technical sciences, and one of the two higher educational institutions that conducts studies in geology in the field of natural sciences, our faculty has recognized the importance of geoenvironmental engineering long time ago. We have embedded the principles of geoenvironmental engineering into our study programs. As of academic year 2005 and 2006, with the start of the so-called the Bologna process, besides implementing geoenvironmental engineering principles to our undergraduate study programs, we also started with three study sub-programs on a graduate level. These are waste treatment and disposal, environmental geology and petroleum, environmental protection in petroleum industry. These study sub-programs strongly rely on fundamental aspects of geoenvironmental engineering. With no further ado, I leave you to interesting lecture of Professor Rowe, with no doubt. Speaking of lectures, unfortunately I have to apologize because my lecture just started and hopefully my students are still waiting for me, so I won't be able to stay with you for the whole time. At the end, I thank Croatian Geotechnical Society for choosing our institutions for this series of interesting lectures that we are having at our premises. I wish all of you a good working atmosphere and a pleasant stay on our faculty. And at the end, I greet you with traditional mining greetings. Good luck. Thank you.
Uvodnim nekim riječima i doktor geotehnici da upoznao na tehničkoj visokoj školi u Beču 1932. tamo završio, da upoznao je geotehniku kod oca geotehnike profesora Karla Percagi. To je naravno ostavilo traga u njegovom daljnjem radu. On je ujedno i prvi doktorant iz područja geotehnike u Hrvatskoj iz 1957. godine, doktorirao kod profesora Šupljuta. Neću nabrajati sve, njegove doprinose, od toga ima izuzetno puno. Ono što je važno naglasiti da je sudjelovao u svim značajnijim projektima u tom periodu, bilo da je riječ o hidrotehničkim objektima, granama, složenijim, plitkim i dubokim temeljenjima, stabilnostima kosina. Dakle, njegov doprinos odrazio se kroz rad u svim renomiranim institucijama u tom periodu, od rada u hidroelektri, elektroprojektu, geoekspertu, kasnije kao profesor Građevinskog fakulteta u Zagrebu i dekan Građevinskog fakulteta u Zagrebu, dugogodišnji urednik časopisa Građevinar. Napisao je preko 150 znanstveno stručnih članaka, objavio 4 knjige koje su svima nama dan danas, što se kaže, pri ruci, iz kojih se puno stvari može i dan danas naučiti i zanimljivo je vidjeti kako su sagledane u samom početku nastajanja geotehnike. Profesoru čast održavamo Nonveillerovo predavanje. Prvo održao profesor Heinz Brandner 2000. godine, nakon toga slijedi čitav niz stručnjaka iz područja mehanike tla i stijene, geotehničkog inženjerstva, stijenskog inženjerstva i danas dolazimo do profesora Kerrya Rowa koji će dati naglasak na geotehniku zaštiti okoliša, dakle geoenvironmental engineering. Pa evo, ja bih zamolio profesoricu Biljanu Kovač-Jezelić da nam da više informacija o životu i radu profesora Kerrya Rowa.
Hello to everyone. I'll try to make some introduction about Professor Kerry Rowe. So Professor Kerry Rowe was born and educated in Australia. He worked as a geotechnical engineer with Australian Government Department for Construction for several years. He emigrated to Canada in 1979 to take up an academic position. He has been working for almost 40 years as a professor at the Western University and the Queen's University, including 10 years as a vice principal for research, being responsible for all research at the university. He presently holds the Canada Research Chair in Geotechnical and Geoenvironmental Engineering at Queen's University in Kingston, Canada. He has extensive research and consulting experience in geotechnical, geosynthetics, waste management, and geoenvironmental engineering, with a special emphasis on the performance of liner and cover systems, the interactions between components of these systems, and the long-term performance of barrier systems. He published over 350 refereed journal papers, 3 books, 20 books chapters, and more than 300 full conference papers. His age index is one of the highest worldwide in civil engineering. Considering the fact that geoenvironmental engineering represents one of the newest emerging disciplines in engineering, and being the author of 3 books, his personal contribution in the field is highly recognized all over the world. Many of us here regularly follow professors' published papers, and in our daily work at the university or in companies, we often consult his books. His work includes the design and/or peer review for more than 130 waste disposal, remediation, hydrology, dam and tunnel projects worldwide. Since it is impossible to elaborate all of the challenging projects in which Professor Rowe has provided expertise, let me mention only a few facts. His work has influenced waste and landfill regulations and guidelines in countries such as Canada, USA, Australia, South Africa. These are now used as a model in many other countries. His expertise is related to the municipal solid and hazardous waste landfills, the landfill siting and site characterization, risk management of landfill gas, the long-term performance of landfill liners and leachate collection systems, the use of tire shreds in landfill leachate collection systems, the remediation of hydrocarbon and PCB contaminated soils, the liners for mining applications, low-level radioactive waste landfills, etc. Besides his teaching and research activities, Professor Rowe has also given a great contribution to the engineering profession. Among many professional activities, I will mention just a few. He is a past president of the International Geosynthetic Society, the Canadian Geotechnical Society, and the Engineering Institute of Canada. He is editor of the highly regarded international journal, Geotextiles and Geomembranes, subject editor of the Royal Society Open Science, associate editor of the Canadian Geotechnical Journal and Waste Management. Besides, he presently serves on the editorial board of 12 other journals and has in the past served for 10 years on the editorial board of Journal Geotechnical and Geoenvironmental Engineering and for 4 years on the board of Geotechnics. He has been recognized by numerous awards, including Stacy Fellowship, EGS Gold Medal, Killam Prize, Killam Fellowship, Leachate Medal, Sir John Kennedy Medal, Professional Engineers Ontario Engineering Medal, the Royal Society of Canada Armanovsky Medal, and many others for significant contributions to the resolution of scientific aspects of environmental problems. He has been selected to present some of the world's most prestigious named lectures, including Giraud Lecture, Rankin Lecture, Manuel Roja Lecture, Casagrande Lecture, Carl Tetzade Lecture, Croce Lecture, and over 80 keynote lectures and conferences. In 2013, the International Society for Soil Mechanics and Geotechnical Engineering created a named lecture to honor his pioneering contribution to geoenvironmental engineering, the ISSMG Kerry Rowe Lecture. Largely in recognition of his contribution to both the research and the engineering practice, he has been elected to the world's oldest and most prestigious scientific society, recognizing fundamental contribution to science, the Royal Society, London, UK. He has also been elected a Fellow of the Royal Academy of Engineering, the Royal Society of Canada, the Canadian Academy of Engineering, and a foreign member of the US National Academy of Engineering, as well as professional societies in Australia, Canada, and USA. This year, he was appointed as an officer of the Order of Canada, Canada's highest civilian honor, for his seminal contribution to the field of geoenvironmental engineering, notably for his pioneering research in waste barrier systems. It was a challenging task for me to select only some of the many highlights from such a rich scientific teaching and professional career of Professor Rowe. Nevertheless, I'm sure that all of us are happy today to be here and to have a chance to listen to the 16th Nonveiller lecture given by Professor Rowe, a world-renowned researcher and consultant who has extensively contributed to the engineering profession. Thank you very much, Professor Rowe, for coming, and to all of you coming also to listen to Professor Rowe.
Well, thank you for a very detailed introduction. It's indeed a very great honor and privilege to have this opportunity to present the 16th Nonveiller lecture. I do want to express my appreciation to the Croatian Geotechnical Society for inviting me to be here, and for this, my first opportunity to visit Zagreb and indeed Croatia. In looking at the past history of the work done by Professor Nonveiller, I noticed that we had a number of areas of intersection, including earth dams and caissons in weak rock. But what I'd like to talk about today, environmental geotechnics, has all been developed since he retired. It is a relatively young sub-area of geotechnique. It includes some very broadly defined areas, including erosion protection, stability in extreme events, management of water in extreme events, and reducing greenhouse gases and global warming. But what I would like to particularly speak to in this presentation are two issues: the protection of ground and surface water, for example, landfill barrier systems for municipal solid waste, low-level radioactive waste, mine tailings, heap leach pads, and deep disposal of high-level radioactive waste will be touched upon at the very end. And of course, the other aspect is remediation of past sins and contaminated land. The presentation has two conceptual parts. The first is looking back at the advances that we have made over the last 30 years in understanding different components of a barrier system. We'll be talking about advective diffusive transport through clay liners. We'll be talking about the importance of leachate collection in landfills and of geomembranes. But we're also going to talk about the system itself and how the various components of the system interact. We'll talk about the interaction between the geomembrane and under and over liners. We'll talk about the interaction with climate, the use of different polymers, and geomembranes in remediation. But first, let us start with some basics. There are two transport mechanisms that we have to talk about. One is advection, and that is the movement of contaminants, suspended solids, be they dissolved atoms, molecules, with moving water or leachate. And this is related to Darcy's law. And to give you an analogy, if we picture this moving walkway in an airport, then the movement of people is going to be related to their concentration, the number of people per square meter on the moving walkway, and the speed of the walkway. So when we're dealing with groundwater, its flux is controlled by something we know very well, the Darcy flux. We'll come back to that. The second mechanism is a molecular process called diffusion. It is the movement of atoms or molecules due to a concentration gradient, and it can occur with no fluid flow. So for example, if we turned off the air conditioning in this room and I opened a bottle of perfume and poured it on this lectern, very soon people would be able to smell it at the back of the room, as it diffused from high concentration at the front to low concentration at the back. And just as perfume can diffuse through air, it can diffuse through water, contaminants can diffuse through soil, and in some cases even through solid geomembranes. And this diffusion process is related to Fick's law. So what happens with diffusion is we have a large number of molecules bumping against each other, and they migrate through some medium, be it a soil, a geomembrane, from high concentration to low concentration. So if we consider the advective transport, it is going to be governed by two things. The first we know very well as geotechnical engineers, and that is Darcy's law, which says that the Darcy flux is equal to the hydraulic conductivity times the hydraulic gradient. Now, if we talk about advective transport, we have to bring in concentration of contaminant. So it's simply the concentration of contaminant times the Darcy flux. And so that flux is related to a resistance. In this case, that resistance is our good friend, the hydraulic conductivity, and a driving force, which is the hydraulic gradient. And if we want to minimize advective flux, there are two things we can do. We can reduce the hydraulic conductivity, or we can reduce the hydraulic gradient. Now, if we talk about diffusion, it's controlled by Fick's law, which looks very similar to Darcy's law. We have a diffusion coefficient times a concentration gradient. So let us talk about these various components. And we're going to start with clay. And why not start with compacted clay? And over the last 3 decades, we have come to really understand very well the hydraulic conductivity of compacted clay. Now, of course, we have, as geotechnical engineers, understood hydraulic conductivity with respect to clean waters through dams, for example, for a very long time. But what is different about contaminant issues is that the hydraulic conductivity is no longer a constant. It can vary because of interaction, chemical interaction with the contaminants in the leachate. But we understand that pretty well now. We've made good progress there. What about diffusion? That is much less familiar to geotechnical engineers. But we have great natural analogues since the last glaciation. For example, in Canada, the retreat of the glaciers laid down thick deposits of clay material overlying saline bedrock. And over the last 10, 12,000 years, salts have been diffusing up through what were clean water, lacustrine deposits. So here is an example showing actual data from a field site where there is a small downward gradient of about 1 × 10⁻11 meters per second in terms of Darcy flux. And we see, despite that downward Darcy flux, contaminants have diffused up more than 34 meters in the last 10,000 years. And what is particularly remarkable is that we can predict that very well with data we obtain in the laboratory in the space of about a week. And we can relate it to a diffusion coefficient for chloride of about 6 × 10⁻10 meters squared per second. Now, what about compacted clay in a landfill? Well, we see it there. It just happens a lot faster. Here are 2 profiles from the Keel Valley landfill in Toronto, Canada, taken after only 4¼ years. And on the left-hand side, the advective transport through this low hydraulic conductivity clay liner is less than 2 centimeters. But in 4¼ years, chloride has diffused over 80 centimeters. And we can predict it with the same diffusion coefficient that we've used for 10,000 years of data. It's not just chloride that diffuses, so too do organic compounds, as you can see here for toluene and ethylbenzene. They've migrated almost as far as chloride. So when you have low permeability, you really have to think also about diffusion. Now, I mentioned that diffusion can occur even when you have flow in the opposite direction. Well, we've seen an analogy to that in an airport if you've been waiting and you see a bored child running the wrong way on a moving walkway. And just as that little boy could run against the flow of the walkway, so contaminants can diffuse against an inward gradient. And all of this is entirely predictable. And as a consequence, a very popular landfill design technique in areas where you have dry groundwater level is what we call hydraulic containment. So here we see a situation where we have a potentiometric surface in an aquifer at this level. Under natural conditions, there's a slight downward gradient from the water table to the aquifer. And if we excavate a hole, put in a leachate collection system, and maintain the leachate level here below the potentiometric surface in the aquifer, well, Darcy's law tells you that water flows from high head to low head, and so water flows into the landfill, albeit very slowly through a clay deposit. And we must maintain that inward gradient if we want hydraulic containment. But we can't ignore our old friend diffusion. We also have to look at what contaminants can migrate by diffusion out of the landfill. And in fact, that is what controlled this particular design. Now, one of the things that will be obvious to you here is that the whole concept is totally dependent on an effective leachate collection system. And we need it to last for a long time. So that brings us to leachate collection systems. And we've made great advances there in the last 30 years. If we go back to the 1970s, in some places the 1980s, and some places still today, what they used was a pile of gravel with perhaps a pipe in it, perhaps wrapped in a geotextile, at a spacing somewhere between 50 and maybe 200 meters, what some people call a French drain system. But this is a disaster, because very quickly you get a reduction in hydraulic conductivity in the gravel, in the geotextile, and as that happens, your leachate mound builds up and you get more contaminant transport through your liner because you have a larger downward gradient. This is a poor design. Don't do it. And one of the reasons it's a poor design is the geotextile that is used to wrap pipes, and there's a good reason for doing it in many applications, is not the right thing to do in a landfill. This geotextile started with a hydraulic conductivity of about 2 times 10 to the minus 3 meters per second. That's pretty good to a geotechnical engineer. But after a few years, that had dropped by 4 to 5 orders of magnitude to 6 times 10 to the minus 8 meters per second. And now it is not effective at collecting leachate. And it's not just geotextiles. Sand laid out as a blanket will clog. At the Keel Valley landfill, in a few years, just a couple of years, it had completely clogged and was part of the diffusion barrier, not part of the drainage layer. This is what we call gravel less than 10 millimeters. So 10 millimeter gravel, and look at it. It's not often you pick up gravel like a piece of concrete, but that's effectively what it's become because of clogging. And this is coarser, 37 millimeter gravel, and you can see it is cemented together. So we have to think about that when we're designing our systems. Those bacteria are not benign. They can work for us or against us, depending on how smart we are. And we have to think about the pipes. Here is an exhumation we did in the early stages of the Keel Valley landfill because the pipe had clogged. Now, why had it clogged? Because they'd never cleaned it. And as you probably know, if you don't clean your teeth, plaque will build up and probably you'll find yourself having a nasty period at the dentist. that doesn't just apply to humans. It also applies to pipes in the leachate collection system. If you don't clean them, a plaque, a biofilm builds up, and then it becomes a solid, and then it becomes thicker and thicker. And in between 4 and 5 years, you can see this pipe is more than half full of clogged material. And here is a piece we've just removed from the pipe. And this is the same piece after it has oxidized. And you'll see it has the appearance of a weak concrete. And that is essentially what it is. A weak concrete formed by bacteria in that pipe in the space of 5 years because they hadn't cleaned it. So what have we learnt? We've learnt that leachate collection systems have a finite service life, but we can extend it by appropriate design, construction and operations. You need a uniform, coarse gravel layer. You need a suitable filter. Geotextiles can become your friend if you put them in the right place. Get them working for you, not against you. Not only should you clean your teeth, you should clean your pipes. And there are techniques available, you can find them on the web, for predicting the service life of leachate collection systems. So we've just seen a leachate collection system should have a relatively coarse, relatively uniform gravel. Somewhere not far below the leachate collection system often is a geomembrane, a sheet of plastic. And as we know, plastic holds water very well, except if it has a hole. So we need to think about holes. And 2 quotes from my old friend J.P. Giroux. All liners leak. And rather than pursuing the unrealistic goal of zero leakage, it is preferable to discuss the limit between acceptable and unacceptable leakage. So the place to begin clearly is holes. And this has been widely studied over the past 25 years. Lots of references in the literature. And what's become a little bit more common, but still not that common, is leak detection surveys. And when you do a survey like that, you discover some interesting things, like the typical number of holes per hectare in the United States is about 5 holes per hectare, with typical quality assurance procedures. But when you put the gravel drainage layer on top, that can easily go to over 20 holes per hectare. Now, I said that leak detection systems can help you identify and therefore fix these holes. But in 2014, in the United States, only 2% of the geomembrane had a leak detection survey. And Quebec, Canada was probably the best. 21% is 10 times better, but still only 1/5 of all of the area was checked. So if you want a low leakage through a geomembrane, the first thing you need is good quality assurance. And that means somebody out in the field who knows what they're doing, who's on site and not in the trailer filling in forms, but there with a pair of eyes watching what's going on. Because a bulldozer blade takes a few seconds to put a hole in a geomembrane and a few more minutes to cover it up if somebody's not watching. There's an old adage that I'll repeat to you: you get what you inspect, not what you expect. So leak detection surveys come in a number of forms. The puddle method is useful when you have an exposed geomembrane, as you see here. And under the right conditions, you can pick up a hole as small as 1 millimeter in diameter. When you have it covered with water, or if you're covered with soil, you need something like the dipole survey method. And when you've got up to 0.6 meters of soil under the right conditions, you can get holes of 6 millimeters or greater in diameter. So it doesn't eliminate the holes, but you can substantially reduce what is there. So if all liners leak, and we should be discussing what is acceptable leakage, what is acceptable? The answer is, it depends. It depends on your particular situation. So if we look at this dam here in Italy that's been in place with a geomembrane as a liner for almost 30 years. There is a geomembrane, and then there is a geonet drainage layer, and then the concrete of the dam wall. And so one could estimate, and indeed because there's a drainage layer there, you can measure what is the leakage. Here is another project, this is one I worked on recently in Israel, of a pump storage seam. It's lined with a white plastic, high-density polyethylene, in this case geomembrane, and that geomembrane is left exposed. This is another dam I've worked on recently, and this is in Ontario, and here you can see a geomembrane that is being covered in the bottom of a dam. So what is the leakage? If we have, as we saw in that Italian case, a geomembrane with a drainage layer adjacent to it, then we can very easily calculate the leakage using Bernoulli's equation. And let's do that, assuming we have, say, 5 meters ahead above a hole. Let's assume we have 5 holes per hectare. Remember, that was the typical value found in the United States with good quality assurance. If our hole is 1 millimeter in diameter, then the leakage can be easily calculated to be 2,000 litres per hectare per day. That's a strange unit, but it's what is typically used when we deal with geomembranes, and it's abbreviated to LPHD, litres per hectare per day. If that hole becomes 2 millimeters in diameter, we've now gone to 8,000 litres per hectare per day. And studies have shown that the median size hole is somewhere between 10 and 11 millimeters in diameter. And that is 200,000 to, say, 260,000 litres per hectare per day. Now, is that acceptable? Well, for a hydro dam, it may be perfectly acceptable. But what if it's contaminated water? Then it may be totally unacceptable. So what is acceptable depends on your application. So what I've tried to illustrate to you so far is that we have made great progress in understanding things like compacted clay liners and their hydraulic conductivity, diffusion through clay liners. We've understood leachate collection systems and how to design them so they don't fail. We've understood how to calculate leakage through geomembranes. And that's great. But it is not enough. It is not enough to understand the components. We have to also understand the system, and in particular, understand how the components of the system interact. Now, this can be very important because sometimes we can get so excited optimizing one part of the system, like a leachate collection system, that we don't think about what it's going to do to the geomembrane underneath it. And that has resulted in failures. And indeed, there are some regulations in the world that were written thinking about components that, when you put the whole system together, are actually counterproductive. They're bad regulations. So let's look forward. Let's look at understanding the system. And a good place to start is with our friend the geomembrane, but understanding how it interacts with what's around it, because it's not often that it is in a dam wall with water on one side and a drain on the other side. It does happen, but not that often. If we do have it, as we just saw a moment ago, and if we take our hole to be 11 millimeters in diameter, our leakage is 256,000, let's say 260,000 litres per hectare per day. Okay, so what if we had a sand instead of a very permeable geonet? And that sand was 10 to the minus 4th meters per second, and I think we'd pretty all agree that's not a bad drain. And in fact, it is a good drain. And the leakage is just the same as with our geonet. Now let's suppose instead of sand, it's a silt with a hydraulic conductivity of 10 to the minus 6. Well, we start to have an effect. There is an interaction between the geomembrane and the soil that reduces the leakage to 100,000 litres per hectare per day. And if it's a till at 10 to the minus 8 metres per second, a till is a well-sorted material. I'm not sure if you use that term in Croatia. It's a very common one in Canada. The tills are deposited by glaciers, and they have a range of silts and sands and gravels and boulders. And that material is not bad. It gets us down to 1,000 litres per hectare per day. 2 orders of magnitude reduction in hydraulic conductivity here gives us a 2 order of magnitude reduction in leakage. Okay, now if a till at 10 to the minus 8 is good, a compacted clay liner at 10 to the minus 9 should be better. And not surprisingly, it's not just a little bit better, it's a lot better. Instead of dropping 1 order of magnitude in leakage, we drop a factor of 20. It's more than just hydraulic conductivity. Hydraulic conductivity is important, but when we get to clay liners, more is involved. So now our leakage is now 50 litres per hectare per day. And if we could get that, we would be really, really happy. That is definitely the zone where diffusion is dominant. The leakage is so small that diffusion is going to control our design. But, and here comes the big but, that assumes that when we cover our geomembrane, it looks like this, and our compacted clay liner looks like this. However, if we leave our black geomembrane out in the sun, even in Canada it gets to 60 degrees Celsius. If you get to Texas, it gets to 80 degrees Celsius. And what that does is it causes water to evaporate from the clay, especially at the top, and migrate to where the airspace is, which is the wrinkles you can see here. These are wrinkles caused by expansion of the polyethylene when it gets hot. And if we do that, what we can end up is this: desiccation of the clay liner. Now, on one hand, you might be tempted to say, well, it's just a few centimetres, what does it matter? Well, it matters actually a very great deal, because now the water can easily migrate through that fractured network at the top over the entire surface. And so we now get an increase in leakage from the lovely 50 we had before to 8,000 litres per hectare per day. All because of construction considerations. This is not probably what the designer expected, but it's what you can expect if you don't pay attention. So what are some solutions? Well, one solution is to use a white geomembrane. Doesn't solve the problem, but it helps because it drops the temperature in our measurements by about 20 degrees on a hot day. What this illustrates is we have to consider the interaction between the liner system and climate. A white geomembrane helps. A GCL, a geosynthetic clay liner, either with or as a replacement for the compacted clay, is a good thing to consider. Oh, but what is a GCL? I haven't introduced that to you, so it must be time to do so. A GCL is a manufactured product. It comes in a roll, as you see here. It comes off the roll, typically 5 to 10 millimeters thick. And in 95% of the cases, it is a layer of bentonite, typically sodium bentonite, not always, but mostly, sandwiched between two geotextiles, and all needle punched together to hold together, first and foremost, so it can be rolled up and easily laid out on site. Now, bentonite on the roll has a low water content. And for bentonite to have a low hydraulic conductivity, it has to be hydrated. So where does it get its water? Well, basically, it sucks it up from the soil beneath it. And a GCL taking up moisture from a good subgrade will typically have a hydraulic conductivity less than 5 times 10 to the minus 11 meters per second with respect to water. And for that reason, we often use a geomembrane together with a GCL on a subgrade as a composite liner. And they've been very effectively used for more than 20 years. But we do need to pay attention here too. It's not just compacted clay that can be affected by our interaction with climate. Indeed, it's to study this particular problem that we first built the Queen's University Environmental Liner Test Site, or QELTS. It's located just north of Kingston in Ontario, Canada. We've built it once, monitored it for 6 years, and then completely pulled it apart and rebuilt it, and we've now been monitoring it for another 6 years. We're studying many things, but the one thing I want to talk about today is shrinkage. So to put this in context, GCLs come in a roll, they're laid out like this, and depending on the manufacturer, there will be different recommendations about how you seal the overlaps. So one manufacturer, a German company, impregnates bentonite in the 50 centimeters from each edge. And they recommend overlapping by 30 centimeters. And that impregnated bentonite provides a seal between the two geotextiles. And remember, geotextiles can be permeable. We need the bentonite to seal it. Now, that's not the only way to do it. Here is a Canadian manufacturer who recommends placing 0.4 of a kilogram per meter of supplemental bentonite between the lower and the upper panel. You can see I folded back the upper panel here so that you can see the bentonite. And they also recommend a 30 centimeter overlap. And here's a third option. This is a US manufacturer who puts in a groove, typically about 7 to 8 centimeters from the edge of the roll. And one is relying on the bentonite that comes from that groove to provide the seal. And this manufacturer typically recommends a 15 centimeter overlap. Okay, well, that's all well and good. Under the right conditions, all of those systems work. Under the right conditions, all of those systems work. Well, what are the right conditions? Well, one of the good ways to find out is to read the manufacturer's instructions. Unfortunately, not only is it other instructions we typically don't read, we often don't read the manufacturer's instructions. If we read them, they would say, whether you use the GCL alone or as part of a composite liner, cover it in a timely manner. Unfortunately, this is a recommendation more honoured in the breach than the observance. Very commonly, composite liners are left exposed for months, and in the case of side slopes, often for years before they are covered. So the question we should ask ourselves, what are the consequences of that? And the answer is, it depends. Let's begin with where we talked about before, what we would like to happen. And what we would like to happen often, in fact, does happen. We put the GCL on top of the subgrade, the geomembrane on top of that, and the GCL sucks up the water And relatively quickly, you get this nice gel-like structure. This has got low hydraulic conductivity. This is beautiful. If it stays like that, we'll be really happy. But if we leave our black geomembrane out in the sun, it is going to get hot. And when it gets hot, not only will water evaporate from a compacted clay liner, it will also evaporate from our GCL. And when it goes into the air, where is most of the air? In the wrinkles, which are where the geomembrane has buckled as it expanded. And when the geomembrane cools, that water condenses, but it doesn't go back to where it came from. So we're going to look at one of the consequences of that, and remember, this is all about weather. It's how things happen in real life. And this is data from our air temperature monitor at the Quelz site. Now, Quelz is at latitude 44 degrees, 34 minutes north. Interestingly, that's a little south of where we are right now in Zagreb. Zagreb, when I looked it up, was 45 degrees, 48 minutes north of the equator. So Canada's not all a long way north. And this is what the weather looks like in our Quelz site. You can see in the summer we can be up to, in this year, about 32 degrees Celsius. In the winter it got down to about minus 28, with ups and downs in between. Now that's the ambient temperature, but the geomembrane is a very different creature. Look at it. It rarely dropped below freezing. Lowest it got to is minus 5. But it got up in this particular year to almost 60 degrees Celsius. And look at those cycles. The ones I've highlighted in aqua and it's light green is when there's a period for it to hydrate and then a very hot period that follows. So our GCL is going to have time to suck up water, then it's going to have a period when it's hot and it evaporates water. It sucks up, it evaporates, it sucks up, it evaporates. Well, what does this do? Here we see a geomembrane specimen, a GCL specimen, I'm sorry. This is a very common GCL. I've even seen it in the labs here at Zagreb today. You can see this specimen starts off parallel to this yellow line and this yellow line. And what we're going to do is we're going to look at some time-lapse photography where we wet it and then we allow it to dry overnight. Then we wet it, we allow it to dry out overnight. And let's see what happens. And you can see after a few cycles, it is no longer aligned where it started. It has shrunk. Okay, well that's all very nice and good. You know that certain clothing items, if you don't look after them properly after you wash them, will shrink. You now know that some GCLs will shrink. Why do we care? The answer comes back to the overlaps. So this is what we would like to see. And here we have our overlap. We have our supplemental bentonite, which provides a resistance against flow between the two panels. And as it's shown there, it's exactly as we would like to see it. But let's suppose that GCL panel shrinks. Once it shrinks away from the supplemental bentonite, now remember that how much supplemental bentonite you've got depends on which manufacturer's guidelines you followed. 3 very different answers you could get. But once it shrinks away from that supplemental bentonite, now we have a clear flow path between the panels, even if an overlap exists when you look at it with your eyes. So you could walk on it and say, oh, that looks all right. What you can't see is that may have shrunk away from the bentonite. Now, in some methods of doing it, that's much less likely than other methods. So think about that. Here's an obvious problem. Now we have a gap. So now we have a geomembrane with a drain beneath it. Does this happen? Well, here's data from our field site. We looked at in the first instance, 4 different geomembranes, in the second instance, 5 different geomembranes. And you can see it depends on the GCL. This GCL2, this GCL4, they've all got the same hydraulic conductivity, they've got the same swell index, but they're manufactured in a different way. And they perform, as you can see here, quite differently when left exposed. After almost 5 years, the shrinkage of this GCL was less than 25 millimeters. We have 300 millimeters of overlap. We do not have a problem. It's great, no worries. What about GCL4? This is one panel, this is another panel. So you can see even for a given product, it depends a little bit on where you're located. But if we place this with 150 millimeter overlap, this GCL4 has this little groove, 70 to 80 millimeters from the edge. And so by the time we've got this much shrinkage, we have disengaged the supplemental bentonite. And so if we had 150 millimeter overlap with this particular sealing, we would have had a problem, well, underneath this picture. If we, in fact this is what we did, had a overlap of 300 millimeters, then this is how much movement you need before you disengage that groove. But you can see we have a problem not here, but here. And you can see that even with a 300 millimeter overlap, it's not enough to prevent a gap. You can see with your own eyes a problem. But of course you can only see that because we took the geomembrane off the top so you could look. If the geomembrane was there, you would not see it. You would not know it was there. So what does this do? We have a large, you might want to call it a permeameter, 1 meter in diameter, where we can study these things. And this particular GCL was placed with a single panel, and for a given gradient, we have shown here what the leakage is. Now, if we put an overlap, 150 millimeters with appropriate supplemental bentonite, this is what the leakage is. The actual numbers don't matter, but you'll notice it's a little less. The reason is obvious, because the supplemental bentonite was very effective, and because we've got 2 layers of GCL where the supplemental bentonite is effective. That's good. Now we looked at what happened if that overlap shrunk so it was only 50 millimeters, and so that the supplemental bentonite was disengaged. So visually it looks okay if you're looking at it from the top. But the leakage increased by a millionfold. This matters. So shrinkage depends on how the GCL is manufactured. It depends on your focal site conditions. But if you want to minimize it, the first and best thing to do is follow the manufacturer's instructions. Cover it as quickly as possible, and if you do that, none of the GCLs will give you a problem. If you can't do that, then you have to be a lot more careful. Now you have to select a GCL to minimize your risk. They are not all the same. You need to ensure an adequate overlap. I would recommend 300 millimeters. You can do something called heat tacking the seams sometimes, and that helps, but it's not a guaranteed solution. A white geomembrane reduces the thermal cycles. It helps, but it is not a solution. The solution is to cover in a timely manner. So GCLs can shrink, but compacted clay can desiccate even faster. So you have to be careful with what's going on in construction. Shrinkage can be minimized by appropriate design and construction. Okay, we've talked about what's underneath the geomembrane. Let's talk about what's on top of it. And if we look at what we've already discussed, we've seen that if we have a subgrade at 10⁻⁶, and a permeable material directly on top of it or nothing on top of it, our leakage is 80,000 litres per hectare per day. If we were putting a cover soil on top of it at 10 to the minus 5 metres per second, so it's a sandy material with a bit of silt maybe, and we've got the same subgrade at 10 to the minus 6, we drop the leakage to about 70,000 litres per hectare per day. Not very much. That cover soil above it generally has very little effect. But what if that cover was thick and of a significantly lower permeability? Where, you might ask, would you find that? And my answer is a tailings storage facility. And here is a tailings dam, which when it's completed will have tailings to a thickness of 110 metres. And because the consultants we work with asked this question, they asked, what would the leakage be if we have a typical 10 to the minus 6 subgrade, the one we've just been talking about that gave us 70,000 litres per hectare per day, but instead of a thin, relatively permeable cover, we've got 110 metres of tailings at 2 times 10 to the minus 6. So they're more permeable in the subgrade, but there's a lot of them. And what happens is the leakage gets very small. We drop to 35 litres per hectare per day. If that tailings goes to 10 to the minus 7 metres per second, we drop to 26 litres per hectare per day. And if it goes to 3 times 10 to the minus 8, we drop to 2.5 litres per hectare per day. That's very good. So leakage depends on what's above and what's below. And I should point out that those tests and leakages were not for 5 metres of head, they were for 150 metres of head. Okay, so we've been talking about holes after installation. One of the important things we need to think about is how we protect our geomembrane. We've talked about it's good to have a coarse, uniform gravel drainage layer. But if we put that directly on the geomembrane, it's probably not going to be very kind to the geomembrane. Well, people recognise that and put on a protection layer, and typically it is a geotextile protection layer. You can see one here. Then you put a gravel on. If we're lucky, it's nice, rounded riddle gravel. But we're not often that lucky. Often it's crushed gravel that looks like this. So what does that do to the geomembrane? Well, to find out, let's build a liner system. We'll put a foundation layer, a GCL, a geomembrane, a geotextile, some gravel, and in our landfill liner simulators, we can load that up to 3 megapascals. Too big for a landfill. Landfill is typically less than 1 megapascal, but for a heap leach pad in mining, even 3 megapascals is not the top end. And we can ask ourselves, how would this drainage layer, either in a landfill, in a heap leach pad, affect the geomembrane? So here is the material being placed, a foundation layer, a nice pristine geomembrane. Here's the gravel that's being used. Now we've loaded it to 250 kilopascals and we're taking off the gravel. And this is the protection layer. And you can see the indentations in the protection layer. As we pull back that geotextile and look at the geomembrane, you can see that those gravel particles have indented through the geotextile into the geomembrane. And in fact, you can appreciate, even if there are no holes, there are some big strains. Now, what I just showed you was with the geotextile at the top of this slide. It's typical of what people use in North America, 600 grams per square metre. But I hope you can appreciate from that last picture, while it may be typical, it's not adequate. On the lower side, we see a geotextile at 2,400 grams per square metre, just to give you a sense of scale. And let's ask ourselves, what's the effect of the mass of that geotextile? Well, if we have none, at 250 kPa, which is a medium-sized landfill, maybe 20 meters of waste, perhaps, something like that, we get strains of 17%. Now, to put that in context, quite some years ago, the Germans, Seeger and Müller, made a recommendation, which I think, in fact, is a very good recommendation, not to exceed a strain of 3%. Well, if we take that as a guideline, clearly 17% doesn't meet it. If we use a light geotextile, we get 10%. A reasonably heavy, roughly twice what is typically used, we're down to about 7.7%. A 2,000 gram, we're at 5.5%. 150 millimeters of sand, we're at 0.2%. Draw your own conclusion. Now, why do we care? If there's no hole initially, why do we care? The answer is, where the geomembrane will fail is where there are tensile strains. And let me prove that to you. Let's take a geomembrane 1.5 millimeters thick. We'll put on a typical North American geotextile protection layer of about 600 grams per square meter. We'll put on a typical drainage layer used in Ontario, where I live, 50 millimeter gravel. We'll take a medium-sized landfill, 250 kilopascals, but this data we'll do at 85 degrees. So that 85 degrees is pretty extreme. It's so things happen a bit faster. And what we're plotting here is the number of cracks in a 0.6 meter diameter specimen versus time after the antioxidants that protect the geomembrane are depleted. I don't have time in this lecture to explain the details of that, but the important point you really need to get is that this geomembrane performed beautifully until about 20 months. At 20 months, we had one crack. One crack doesn't sound so bad until we remember it's a 0.6 meter diameter specimen. And we're used to talking about holes per hectare. So what does that mean in holes per hectare? It means 35,000 holes per hectare. That's getting to be a large number. But even more importantly, once the cracks start, they grow exponentially. So this is at 20 months. At 24 months, we have 400,000 holes per hectare. At 25 months, 1.4 million holes per hectare. And at 25.5 months, 2.2 million holes per hectare. And that's what the geomembrane looked like. I think we can probably agree it has reached the end of its service life. You see the light because we're sitting on a light table. So there are quite significant cracks there, both in width and in length. So with a 600 gram protection layer, we've got strains up to about 15% and 2 million holes per hectare when it starts to crack. And that happened within 3 years. This is exactly the same geomembrane under exactly the same conditions with one exception. We used a 150 millimeter sand protection layer. And it looks as beautiful as the day it was put in. And that test has been running now since 2006, so 12 years, not a problem, performing beautifully. It's not about the geomembrane, it's mostly about what we as engineers do in our design. Your protection layer is critical. So, with a very coarse gravel drainage layer, we need a very thick geotextile, and I say very, very thick, or, because that's going to be very expensive, maybe a sand protection layer. Now, another way we can get strain is from the consolidation of the waste. As geotechnical engineers, any of you working with piles and soft ground are probably familiar with negative skin friction. When the soil that's consolidating starts to drag down the pile. Well, we have a similar situation for a liner system in a landfill. We put waste on top of the liner system. The weight of that waste itself tends to drag down because of the friction between the layers, and as it consolidates and degrades and settles more, we get further down drag. And that induces tensions in our geomembrane. And there are ways to calculate that. And here you see some results for a particular case. I won't go into the details of the case, it's just been published in the Canadian Geotechnical Journal. But you can see near the top of the slope, these are breaks in the slope here. Near the top of each of these slopes, you get the maximum strain. And what is it? Well, with one-to-one slope for this particular case, it's almost 9% at closure, and with degradation of the waste, it increases to about 19%. Compare that to Seeger and Muller's 3%. 2-to-1 slopes, at closure we're at 4.4, after waste degradation 11%. With 3-to-1 slopes, life looks a lot happier. We're at 2 and 2.1%. So once you go over 3-to-1 slopes, you have to pay a lot of attention to what the strains may be in your particular geomembrane. And that may mean you have to use some reinforcement to carry the load so it's not carried by the geomembrane. So we're getting towards the end here. I have been mostly talking about leakage, but I want to come back for a little while and talk about diffusion. The traditional geomembranes are excellent diffusion barriers to most contaminants in a landfill. Anything that's ionic, salts. I've been running a diffusion test continuously for 25 years and have found 0 salt getting through a geomembrane. But for other contaminants, such as benzene, toluene, dichloromethane, TCE, PCE, for a typical geomembrane, I only have to run a test 1 to 2 weeks. And it's significantly through the geomembrane. Now, what this has caused is the development of new products designed to deal with this situation. So let's look at a diffusion test. Here we have a cell, it has a geomembrane here, a source of contaminants on this side, clean water on that side. We monitor the decrease in concentration in the source and the increase in the receptor. And in particular, what I'm going to highlight for you, since maybe many of you have never seen this, is a co-extruded geomembrane. It has a traditional polyethylene outer core. It could be linear low density or high density. But in the core, in the center, it has a material called ethylene vinyl alcohol, or EVOH, which is particularly good at containing or stopping those contaminants that easily get through polyethylene. And so let's look at some data. Here we see a plot looking at the yellow curve for PVC. And you can see in this test, within 2 weeks, we've reached an equilibrium. The concentration in the receptor is the same as in the source. For linear low polyethylene, it's much the same. This is high density polyethylene doing a lot better, and this is the co-extruded EVOH. This is the same data, just plotted on a different time scale. And you can see that after about 240 days, the HDPE comes to an equilibrium. A lot better than PVC and HDPE. But look at the EVOH layer. After 1,000 days, it's still got a long way to go. We've been running that test now for 8 years, but we predict we're going to have to run it for 16 years before we get to equilibrium. Compare 16 years to 14 days. Not all geomembranes are the same. Just to give you an example of how this can affect your design. Often, we have to build over soil that we've tried to clean it up, we've made a good effort, but there's a limit to how much you can clean it up economically. And now we want to use it, we want to build on top of it. It's what we call a brownfield site in North America. Let's suppose we want to build a 5-metre high warehouse. That the mechanical engineers tell us that 25% of the air will be changed every hour. We have a 0.3 metre thick concrete foundation with some cracks in it. Its porosity is 0.005. We put below that a vapour barrier or geomembrane. We have a 0.3 metre thick foundation layer, and below that some hydrocarbon contaminated soil. In the US, a typical guideline is the NIOSH, and in that building you shouldn't exceed about 3 milligrams per cubic metre. As you can see from this slide, it matters what we selected as our vapour barrier or geomembrane. If we use 1 millimetre PVC, we're at 37 milligrams per cubic metre. If we use 4 different polyethylene thin products, we're somewhere between 18 and 26. Let's say 6 to 8 times the recommended limit. We get to 0.8 millimetre thick geomembrane, that's HDP, we're just getting below it. 1.5, yeah, we're getting reasonably safe. But a 0.53 millimetre thick co-extruded is 4,000 times lower. Less material, much better performance. Not all geomembranes are equal. Now I'm going to finish off by a few words about radioactive waste, because I gather that's of some interest in this part of the world, as it certainly is where I live. We'll start at low level and then we'll finish off with a few words about high level. So if we have low-level radioactive waste, we need a good liner and a cover. They're typically disposed of in a secure landfill facility. But you need a very long service life. In Canada, we require 500 years after you've finished filling the landfill. You have to minimize the strains in the geomembranes that we've just been talking about. You have to minimize the risks of desiccation, shrinkage, whatever, in your clay liner that we've talked about. And you need to pick the right materials. You need to be very wise in your selection of the particular geomembrane and the GCLs. They are not all the same, even if the basic specifications look the same. And you need excellent, full-time, knowledgeable quality assurance. Remember, you get what you inspect, not what you expect. So the service life of a geomembrane in a low-level nuclear facility could be reduced if there was significant heat generation, but that is not likely in low-level nuclear waste. So we can pretty well eliminate that. However, sometimes people like to dispose of low-level waste in a concrete or cementitious matrix. That can have an impact on the pH of the leachate, and you need to think about how that will affect the service life of your geomembrane. Again, not all geomembranes are equal. They have different antioxidant packages. Some will be much better for high pH than others. Then there's the obvious one: what is the effect of irradiation from the waste? So let's talk about that, because quite a bit of work's been done on that question over the last 20 to 30 years. And the effect of irradiation from low-level nuclear waste, even high level, is very similar to what you get from ultraviolet radiation. And the biggest impact is going to be the total absorbed dose that the geomembrane experiences. The dose required to cause a drop in break strength or elongation by a factor of 2 is about 2.6 megarad. Let me tell you, when you're dealing with low-level nuclear waste, that is a very large number. At high doses, the mechanical properties change due to irradiation by a process called chain scission. That is more or less the same process that affects most geomembrane degradation in an environment with oxygen. The geomembrane becomes hard and brittle, and it will stress crack. Now, a very recent paper, only just published in Geotextiles and Geomembranes, did a nice study that showed that alpha particles only get to a depth of about 0.028 millimeters. Beta particles get to a depth of about 0.5 millimeter. They also indicate in this paper that radiation from typical low-level nuclear waste exposure had negligible effect on the depletion of the antioxidants, even if the dose was multiplied 100 times and the service life required was 1,000 years. So that's basically a pretty good news story. And this particular group, in another paper that was published a year ago, predicted a service life of a 2 millimeter geomembrane, let's call it, of 2,000 years. They predicted in excess of 1,975 years at typical liner temperature of 15 degrees. So, in round numbers, 2 millennia. There are a couple of other generalizations we can take from what's been published. You need to ensure a suitable resin, antioxidation package, and carbon black. That's what I've been telling you, that not all geomembranes are equal. A thicker geomembrane is going to be better than a thinner one, because remember, the alpha and beta particles have limited depth of penetration. You again have to minimize tensile stresses. And you can lower the radiation dose by how you design it and providing additional shielding. So I gave you one prediction of how long a particular geomembrane would last. I'm going to give you another one. This is a geomembrane we tested for 17 years to come up with these projections. And for this particular 2 millimeter geomembrane, we're predicting, let's say, about 900 years at 35 degrees Celsius, over 1,100 years at 20 degrees Celsius, and over 2,000 years at 10 degrees. So there's a completely different study to the last one, but you can see generally consistent findings for high quality products and negligible tensile strains. Let's conclude by looking very briefly at high-level radioactive waste. And this is very important to us in the province I live in, Ontario, because 50% of our electricity comes from nuclear. We have 5 plants with 22 reactors, and since the 60s, we've generated 2.7 million used nuclear fuel bundles. And currently, they are sitting in interim storage at those facilities very close to Toronto, which has 6 million people. It would make sense to do something else with it. And the concept that's being considered is deep burial. And by deep, we mean more than 500 meters. So here is a schematic of a facility. If we blow up a little part of that diagram, we see a placement room as visualized, and we can see the components. There's a canister with the fuel rods. We have a bentonite buffer box. We have a spacer block, and we have a gap-filling bentonite. So something we've been talking about quite a bit, bentonite comes into play very importantly in this type of disposal concept. And then we have the host rock. Here you see a blow-up of the bentonite buffer box. So we are in fact actively doing research on this for the Canadian Nuclear Safety Commission. I don't have time to go into any of the details, but some of the questions we might be looking at include: how does the bentonite interact with the bedrock groundwater chemistry? Because for the sedimentary rocks in southern Ontario, they have a high salt contract. 300 grams per litre, 8 times the concentration of seawater roughly. Looking at how the swelling pressure, the seal gaps, changes with time. Looking at how the hydraulic conductivity changes. And what is the effect of thermal gradients? Because here is a situation where we do have to think about what is the effect of heat. So to conclude then, there have been great advances in the use of geosynthetics in dams, municipal waste containment, mining, and low-level radioactive waste containment over the last 3 decades. We've found that environmental geotechnics can reduce impacts and improve the environment by appropriate compacted clay liner design and construction. And remember, I've tried to emphasize that design is critical, but construction is absolutely critical. What you do in construction can ruin the best of design drawings. Design for minimizing impact due to diffusion. Design leachate collection systems that are going to last. Understand that leakage through geomembranes is a function of the number and size of holes, and that therefore you need excellent quality assurance. This is not the place for a client to save money. If they don't have good quality assurance, they have no assurance that they have what they paid for. Electrical leak detection surveys should be used much more. They cost money, but if it's an important project, you should be doing it. And you need to calculate the leakage that you can expect and assess if it's acceptable. You need to consider the interaction between the components of the liner system. How does a composite liner, which is a geomembrane and a clay, interact? And there's various interactions. We've talked about hydraulic conductivity. There's another very important parameter we didn't have time to talk about called interface transmissivity. We need to think about the interaction of the system and the climate. I focused today on the climate during construction, but in many projects we also have to focus today on climate change. The interaction between the drainage layer and the geomembranes. The effect of consolidation of the waste and degradation on geomembrane strains. We're seeing more novel geomembranes being produced, not just your traditional black plastic. These are being developed for a range of reasons: to provide better environmental protection, to give longer service life, to give better performance at higher temperatures, to give better performance in different exposure conditions and solutions, to improve leak detection, to mitigate residual contaminants in brownfield sites, to remediate contaminated soil, and the containment of low-level radioactive waste are just a few examples of how some of the more complicated geomembranes being produced today are being used. Now, I've skimmed over a great deal of work in the last hour and a bit. Couldn't have been done without a lot of support, both financial and in-kind, from a large number of manufacturers, consultants, and regulatory bodies, and installers and contractors. Also, the work I've talked about is not all my work. It's the work of a team of people, a large team of people in our geoenvironmental group. And I'd like to conclude by thanking again the Croatian Geotechnical Society and thanking those who have helped me in getting this particular lecture together and to be here with you today. And I thank you for your patience and attention.
Thank you very much, Professor Kerry Rowe, for this very interesting lecture. It definitely gives us a lot to think about kind of plans, and I hope this lecture will give us a lasting picture for us without. Thank you. And definitely we have a lot of questions to think about. Maybe there are some at the time that somebody would like to ask Professor. Yes, please.
My name is Mesut Mladic. I'm working at the University of Osijek. The geosynthetics also for landfills. So there was one subject you touched related to tensile strain in geomembrane, especially on slopes where you have change the concentration change there. There are also other similar situations where we are aware of the tensile strains that are developed, also in terms of mechanical or thermal reasons. And temperature drops down, then it gets stretched. So I have two questions. First, why do you think that 3% of allowed tensile strain is the limit? Can you reach a lot more? Is it only due to safety against yielding or small features that can minimize the effect of permeability? And the other is, can we, and under what circumstances, count on stress relaxation in this case of?
Sorry, I missed the last word. Count on.
Relaxation of stresses.
Thank you. Okay, very, very good set of questions there. Yeah, there are definitely other mechanisms that will give you strain that I didn't have time to talk about. I just picked two. Differential settlement is another very obvious one. But to the two key questions, the first was, why is it that I believe that 3% is not a bad value? If you look at the literature, there are two numbers available. PEGS had 6%, Seeger and Miller 3%, and Seeger and Miller's was basically a part of a discussion or a paper dealing with indentations. Why do I think it's not a bad value? Because we do a lot of tests and we are running them for long periods of time where we're actually simulating liner systems and monitoring how long it takes under different circumstances for cracks to occur and monitoring what strains they occur at. And we've been getting cracks at as little as 4 to 5% strain. And therefore, since we've observed cracks at between 4 and 5% strain, I don't believe 6% is an adequate limit. I've never seen a crack below 4% strain. So right now, that 3% is looking pretty reasonable to me. Whether I will have the same answer in 10 years' time, I don't know, but we're finding that once we get down to around 4 or 5%, things seem to slow down an awful lot. So it's definitely a lot better. Clearly, the lower the strain, the better. The second question is a very, very interesting one, and one that prompted me to do the last 20 years of work on geomembranes. Because if we go back, there has been a debate about whether we even have to worry about strains because of stress relaxation. And there were various people hypothesizing that, in fact, you didn't have to worry because stress relaxation would make it go away. So we said, let's find out. Let's build some cells, let's load it up, put in a leak detection system so that we know when it cracks, and see what happens. And if we'd been unlucky, those tests would be still sitting there today doing absolutely nothing. I mean, it'd be good for the geomembrane industry, but the PhD students wouldn't be happy. However, we found very quickly that they will crack. As I showed, at 85 degrees, they can crack in the space of about 3 years. And that's from a fairly high stress crack resistance. From memory, it was 800 hours stress crack resistance. We find that as we lower the temperature, it takes longer, but you actually crack at lower strains. And the 5%, 4 to 5% that we've observed is at temperature of 55 degrees C. So we are seeing things slow down as you get to lower temperatures, but we're not seeing stress relaxation solving the issue. We're still seeing stress cracking. So hopefully that answered your question, but it's a great question.
Thank you very much. Do we have some other questions at the time? Thank you. Yes, please.
get one, you can ask me again. So the first question was about prescriptive versus performance-based design. Prescriptive design has the advantage it is simple. You simply write down what you want. I want a 1.5 millimetre thick geomembrane. I want, say, 75 millimetres of compacted clay at less than 10 to the minus 9 metres per second. I need a leachate collection system of such and such a grain size. It is simple. However, it is not necessarily appropriate to all situations. In fact, it's probably not appropriate to a lot of situations. In some cases, that prescriptive design will be gross over design, and in some cases it will be gross under design, because a barrier system doesn't live in isolation. It needs to be considered in the context of the geology and hydrogeology of the area. It especially needs to be considered in terms of the size of a landfill. So let me give you a contrast to a purely prescriptive design to what we actually have in Ontario, which was promulgated 20 years ago in 1998, written in 1995. And it has two aspects to it. One you might call prescriptive, but it's a different type of prescriptive to your typical prescriptive. It says, under certain circumstances, which we'll get to, you can use a single line system with a geomembrane that's 1.5 millimetre thick and a compacted clay liner, a certain thickness, and it says you have to have a certain thickness of natural attenuation soil. And it defines for you the characteristics of the geomembrane that you need, and it defines for you the leachate collection system that you need, and it says you can use this for landfills up to a certain number of tonnes per hectare. But once you go beyond that, you can't use it, because it recognises that there is a limit to what you can do with a single liner system. It then gives you a second option. If you're more than this limit, then you can go to a double composite liner system, and it defines very clearly the material properties that are needed, and it says you can use that up to another limit. But if you go beyond that, you can't use it. And it has some climatic controls on it. It says you can use it provided there are certain climatic conditions. If you don't have those climatic conditions, you can't use it, because it recognises hydrogeology, it recognises the climate's important, it recognises that the thickness of the waste is very, very important in terms of the performance of your liner system. And then it has a whole lot of details that if you do any of these things, you have to talk about wrinkles. I just briefly touched upon wrinkles today, but you've got to demonstrate that you're going to keep that number of wrinkles very low. It's going to talk about leaving your liner exposed. So there's a whole lot of checklists that you have to go through that deal with many of the things we talked about today. But it also says, if you don't want to use this system, let's suppose you wanted to use hydraulic containment, you can use that. But you have to do the calculations to show us that it is going to meet our performance criteria. So what it requires is two things. It requires that you have engineers who know how to do this, and it requires that you have regulators who know how to check it. That is the downside of a performance-based design, is that you need people both on the design side and on the regulatory side who are knowledgeable to actually make sure that the rules are followed. So that was the answer to your first question. I've forgotten what the second one was.
What about different practices in different countries?
Well, definitely in terms of regulation, I've just given you one example. Of course, US, it's got a subtitle D and subtitle C, which is a core different approach. Other countries have different approach. Australia, the province of, or the state of Victoria, because of a problem that they had a few years ago, have recently revamped their regulations. They've got some quite different semi-prescriptive, but with a lot of detail on what you have to provide in terms of liner performance that you don't have. And what's really important there is that they require that there be an independent, knowledgeable assessor who checks the design and who's out there checking the construction. So they have actually caught up with the need to make sure that you have appropriate checks on what's going on. This is taking it out of the regulator having to do all of that checking. It's putting it in the hands of an independent body selected by the regulator. So there are many different regulatory structures. I think the ones that are going to give you the best result will have knowledgeable people implementing them and flexibility.
Thank you very much. Any more questions? If not, we can continue afterwards here at Landfill. We will have the opportunity to ask more in detail. So, thank you once again on behalf of Croatian Geotechnical Society for this interesting lecture, and I would like to give you a small gift just a second. So this is a plaque of gratitude for you as a Nonveiller lecturer, and also you will receive a small gift item of a candlestick that belongs to every Nonveiller lecturer. So
Thank you very much.
To remind you of Croatian Geotechnical Society, and the time is 20.
Let me take the gear off.